So this is part 2. We're going to kick in with example 3. We've been picking u to be x at first. So u equals x, and we did dv as everything else. In this case, maybe like natural log of x dx. Let's think forward a little bit. Whatever you pick for dv, you have to take the antiderivative of. So you have to know its antiderivative and know it's integrable. Natural log of x, what's the antiderivative of that? I have no idea. In fact, we won't know until example 4 how you can go about that, because it's actually itself part of integration by parts. So we don't have that yet under current techniques. So if you can't do the antiderivative, then making it dv is probably not your best choice. We'll actually make log of x our u. So the theme is, if you can't do dv because we don't know its antiderivative, or it's more difficult than we care to, then we choose it as our u, because I know we can antiderive x dx. That's no big deal. So let's do the derivative of u, the antiderivative of x, as shown here. And then what we'll do is our uv minus integral v du. So here's the original. uv is that half x squared log of x. And then the integral of v du, if I just pull that 1/2 out front, that minus integral of v du, then you have the 1/2 x squared times du, which is 1 over x dx. A little simplification there goes a long way. So now we can take that x squared over x, cancel, make it x, which is a nice easy derivative. And that's everything just kind of unfolding. You're good. I mean, you can stop with that step right there, where if you're wondering where that 1/4 comes from, the antiderivative of x is 1/2 x squared, and I just put the 1/2s together as 1/4. But that's it. That's the process. So now we need to talk about natural log of x. I mean, it's worth knowing. That is one we can actually memorize if you like, but it's nice to know it's one of those you can do by parts. And we're going to talk about this lipit thing here in a minute, the way of memorizing what to pick for your u. And actually, logs are the first thing we choose to be as our u. So we're going to do that again. Use natural log of x. dv is 1 dx. Now that one is new. There isn't anything. The u that you pick is, in this case, log of x. dv is everything else and dx, so it always includes dx. Well, there's nothing else except 1, a coefficient of 1. You can even write this dv equals dx. You just have to know the antiderivative of that is just x. And then the derivative, of course, natural log of x, that's no problem. Let's do our uv minus the integral of v du. And there's uv minus the integral of v du. And I kind of crossed something out. That v du piece is actually x times 1 over x dx. And what happens is those cancel, and that's where this 1 comes from. So that's just so you can see where that popped into play. And then we'll keep going from there. Integral of 1 is just x, and that's it. That's actually our antiderivative of natural log of x. It's x ln x minus x. You can try and remember, or just know that it's a perfect candidate for integration by parts, because log becomes our u, the dx is our dv. The lipit thing I'm telling you about is this. Logs are your L, I is inverse trig, P is polynomial, E is exponential, and T is the trig. And that's the hierarchy of what you pick to be u. So on the left, the first thing you pick to be u is any log function. Next in line, if you don't have logs, you look for inverse trig functions. That's your next candidate for u. We run into that too. And then polynomials are your third, exponentials, then trig functions. And what you'll find out is those are kind of decreasing order of difficulty for taking the antiderivative. We know the antiderivative of trig functions and exponentials and polynomials. That's why they're at the end. Logs and inverse trig functions are more difficult antiderivatives. So you're noticing we pick those to be u first so that we don't have to deal with their antiderivatives if we have the option. All right, so next, let's jump to 5. This is a good one. Let's put our lipit to test. This is inverse trig arctangent of x. That's our second option. We want to pick that inverse trig to be our u. That leaves dx to be our dv. And so let's take a peek at that. By the way, remind me to revisit the integral of tangent of x. That's something I want to keep in mind. Here's u. If it's arctangent of x, the integral is 1 over 1 plus x squared dx. I want to have that memorized. dv then has to be dx. The antiderivative is just x. So there's uv minus the integral of v du. And I haven't done anything special. You're trying to find out, here's v, and then du is the rest of that thing. So all's counted for. uv minus the integral of v du. That's a stopping point. We're interested in now, okay, what do I do with this? That last integral is, I still have to be able to figure this out. And so if you look closely at that, that one, if you could see it, there's a u substitution available there. The u substitution on this one, if I make u the denominator, 1 plus x squared, its derivative is 2x. Well, I don't see a 2x up here, so it's going to have, there must be a 1/2 in the antiderivative that makes that possible. So when we look at this one, it's a u substitution. You can do it longhand if you want, but there's 1/2, 1 over u du. So if you want to do u equals 1 plus x squared and work it all out, you're going to get this for your u substitution, 1/2 the integral of 1 over u du. And then you'll take the antiderivative of that, which is natural log of u. And I'm going to go ahead and, I think, just put that in there. The u is 1 plus x squared plus c. So I'm just using u as x squared plus 1, letting you figure all that out. Sorry, no pun intended in that case. And that's it. This is our antiderivative. We are done. You can simplify, factor, do some other things. But again, this is a type of antiderivative you want to have pretty well down. Actually, I would love it if you could make the leap right from beginning to end here without having to do anything. Just knowing, the u is 1 plus x squared. The derivative is 2x dx, and I don't have a 2x on top, so there must be a 1/2 out front. And knowing that 1 over u, the antiderivative, is natural log. Those are things that kind of need to run through your mind on that type of problem. All right, we're cruising forward. I think, let's see, what else do I have going on the sheet? Down below. All right, let's do number 6. Sorry, that just popped up and wasn't paying attention. Lippitt says logs, inverse trig functions, polynomials. So we do u is our inverse trig function rather than the x because it trumps it. It's further on the left of Lippitt. dv then is x dx. I went ahead and put in the du and v, which are pretty quick and easy for you now. Let's go ahead and run this through. Let's get, there's our uv minus the integral of v du. And this one's different. Notice that x squared over x squared plus 1 in that last antiderivative. That is different than what we just ran into in the previous problem. This opens the door to one rule that we need to know about long division. You use long division whenever the degree of the numerator is greater than or equal to the degree of the denominator. That's what we've got here. It's equal, but at a higher degree we'd also think about using the long division to simplify it. So we are going to divide those bad boys, and here's what it simplifies to. So there's uv again, and I'm going to put uv so you can see all the parts, minus the integral of v du. In this part, we just rewrote this blue blob as this with that long division. Okay, so we did 1 is the result of that plus -1, our remainder over our divisor, x squared plus 1. So we just rewrote that. So there's uv minus our rewritten v du. And then we're going to go ahead and integrate that in pieces. So we're going to bust that up into the arctangent. Let's see if I can get us all to squeeze in here. This is a little bit tough to see. Here's uv again. I'm going to keep notating where that's at. Okay, still uv. And then what we did is that integral above is we broke it into 2 pieces. And so the left part, the integral of 1/2 of 1, antiderivative of that is just 1/2 x. And then this last piece here, the -1 over x squared plus 1, that's just the inverse arctangent. Now, don't want to forget the 1/2 as well. But that's arctangent. The integral of -1 over x squared plus 1 is arctangent, but it's negative because of the negative in that. You could have factored that out if you like. So there it is. And then plus c at the end and you're set. So it's really tiny. So can't do much to clean it up. You could do some factoring, but we have long division that we have to incorporate into this too. That's enough for part 2. There's a little bit more. Oh, don't worry, that's a plus, that minus a negative, just to keep you to guessing. I guess I could get an example 7 in there in just a minute here. We want to do inverse secant as our u because it's an inverse trig. The derivative of that is a little tricky. This is one you want to know if you don't already. Okay, it's 1 over the absolute value of theta times radical theta squared minus 1. So I thought I'd put this one out here for you just to peek at, hit pause, and look at it as an option. The biggest thing about it isn't the separation into its parts. You can see those, the uv minus the integral of v du. I'm sure you can follow that part. Here's uv and here's the integral of v du, and I left it all separated, so hopefully you can see it pretty well. Might need to look at your derivative of inverse secant and keep that in mind. But the simplification of this, that theta squared on top, what do we do with this? This is a little new. Okay, so here's pulling out the 1/2 and putting the theta squared on top. thing we can do is we can actually cancel the theta squared and the theta in the bottom, but you know that there's this restriction. Theta has to be positive with that absolute value. That's okay. What we can do is actually just put an absolute value on the theta on top, and we're good to go. Okay, so that still cancels. You just want to preserve that positive nature of that integral. And if you look closely at that one, that's a nice u substitution. There's, so we can follow this part, that u substitution, the denominator, that theta squared minus 1, we're going to make our u. And then that's instead of square root using 1/2. So look at that, theta squared minus 1. If you do du, that'd be 2 theta d, 2 theta d theta. But I need to pull out that 2 and make it 1/2. Okay, so there's a 1/2 that's part of it. So if you want me to write that in, that might help. This is a 1/2 du equals theta d theta. And that substitution gives us what you see on the other side. And we can antiderive that. I'm going to put the whole thing on top here. Here's uv again, uv. And then minus that whole integral of v to u after u substitution. There's the u still in there. I just want you to see from this bottom piece down here, the transfer up here to the top. Okay, that's the antiderivative of 1 over u to the 1/2. And then a little bit more just to close this one out. There's uv again, just keep tagging along. The antiderivative of u to the 1/2 over 1/2, we multiplied that 2. This one divided by 1/2 becomes a times 2, and 2 times a fourth is 1/2. That's what that's coming from. And then that's a radical u instead of u to the 1/2. And that's theta squared minus 1. That's u put back. That's the end of it. Pretty tough antiderivative, but we'll get better at those. It's just knowing what u to pick, breaking it up, knowing when to do long division, when we still have to do u substitution and integration by parts. So this goes on and on. Let me know how I can help.